Christopher.
Hi, I'm Cheyenne Dawson.
I'm Shayna Shelton.
And I'm Danielle Gamble,
And we're
Group
Group
4.
4.
And this is our chemistry QEP project.
We'll be covering subtopics 6.3 through 6.7.
6.3 was all about naming ionic compounds. When you're naming an ionic compound, you need a metal, such as sodium, and a nonmetal, such as chlorine. When forming the name for this compound, you keep the name of the metal as is, so you just rewrite it as sodium. However, for the nonmetal, you take the first syllable of the nonmetal, and then you drop everything after the first syllable and add IDE. So the chlorine becomes chloride. So altogether you have sodium chloride. Now, this is the typical way to name ionic compounds, except when you're dealing with a compound that contains a transition metal, because a lot of transition metals have what's called a variable charge, meaning they have more than one charge. So for example, copper here can have a +1 charge or a +2 charge, and which one you use depends upon the charge of the nonmetal that it's being paired with. So if you wanted to do copper chloride, and you want to use the chlorine as we used above, you write copper, which is the metal, the same, and then because chlorine has a -1 charge, you have to balance that out with a +1 charge. So you would use the Roman numeral 1 to indicate that you're using the copper with the +1 charge, and then you would write chloride as the same as you did here. Now, when doing the formulas for ionic compounds, if the charges balance out like they did for sodium chloride or copper 1 chloride, you don't have to worry about writing the subscript. So you just put the symbols together, so Na and Cl together and CuCl together. However, when the charges don't balance out, you have to add a subscript. So like here we have lithium and nitrogen. Lithium has a +1 charge and nitrogen has a -3 charge. So once you write the symbols for both elements, you then have to basically flip the charges. So you need a 3 for the subscript of lithium, which means you need 3 lithiums to balance out with the 3 charge of the nitrogen. So that's why we have Li3N. So just a quick recap with problems. Here you have Ag, which is silver, and P, which is phosphorus. And when you put those together, you get silver phosphide. Again, we changed the phosphorus, which is the first syllable, and added ion, which is how we got this. For letter B, we have lead and sulfur. So lead is a transition metal that has a variable charge, like copper did over here. And so we have to write the name of the element, and then we use the Roman numeral 2 to balance out with the -2 charge that sulfur has. So you have lead, and then Roman numeral 2, and then sulfide. So we do the same thing that we did with phosphide and chloride, dropping the rest except for the first syllable and adding IDE. And that is how you name ionic compounds and write their formulas. 6.4 was all about polyatomic ions. A polyatomic ion is a group of covalently bonded atoms that have an overall charge. Now, most polyatomic ions are made up of nonmetals bonded with oxygen. As you can see, some here, most end in 8, like sulfate or nitrate. But if it's missing one oxygen, then it usually ends in ite, like sulfite or nitrite. There are some exceptions, like hydroxide and cyanide. Also, most polyatomic ions have a negative charge of either -1, -2, or -3, with the exception of ammonium, which has a +4 charge. Now, when you're naming polyatomic ions, it's pretty much the same as naming any other ionic compound. So if we use barium and sulfate, and we want to put those together, we have to look at the charges to make sure that the charges are balanced, which they are. Barium has a +2 and sulfate has a -2. So you would just write the two symbols, the Ba and the SO4. And that's how you write barium sulfate. Now, if the two charges aren't balanced, you have to do the same thing as with any other ionic compound. So you'll write the first symbol for aluminum and then the symbol for hydroxide. And because aluminum is a +3 and hydroxide is a -1, you have to basically flip them because you need 3 hydroxides to balance with the 3 for the aluminum. And when you write that, you put this symbol for hydroxide in parentheses. And because we need more than one, you have to put the subscript outside of these parentheses. So this will be how you write aluminum hydroxide. Now some practice questions. If we ask you to write the formula for the following ion compounds. Aluminum chlorate, you see here the symbol for aluminum Al, and then chlorate is listed here, ClO3. And aluminum has a +3 charge, as we discussed earlier. So that's why the chlorate is in parentheses with the 3. We pretty much did the same thing for ammonium oxide, magnesium bicarbonate, sodium nitrite, and copper sulfate. With polyatomic ions, the most important thing is to make sure that you name the correct polyatomic ion, because it's easy to mix up like sulfate and sulfide or nitrate and nitrite. And that's all for polyatomic ions.
Subtopic 6.5, molecular compounds and sharing of electrons. Molecular compounds contain 2 or more nonmetals that form a covalent bond. Since nonmetals have high ionized energies, valence electrons are shared by nonmetals atoms to achieve stability. The valence electrons in molecules are shown by using electron dot formula, also known as the Lewis structure. So here we have, I believe it's fluorine 2, and you find it on the periodic table, group 7A. That's how you know that it's 7, and it's times 2 equals 14. So here you have fluorine, you have 7 dots. And also connects to the other fluorine that has 7 dots to come together. And then over here, name each molecular compounds. So for problem A, it's SiF4. Si is silicon, F is fluorine, and 4 is going to be tetra. If you look right here, 4 equals tetra. So the result would be silicon tetrafluoride. IAD is added because it's a molecular compound. And for the rest of them, IBr3 is the same thing, so iodine tribromide, and that ends with IDE. CO2, carbon dioxide, N2F2, dinitrogen difluoride, N2S3, dinitrogen trisulfide. And also, if you look here, there's the key. And that's how I got the tri, di, tetra, and mono.
Subsection 6.6 is entitled Electronegativity and Bond Polarity. Electronegativity is defined as the ability of an atom to attract shared electrons in a chemical bond. With covalent compounds and ionic compounds, covalent compounds are the formation of 2 nonmetals. Their electrons are equally shared. With a nonmetal and a metal, or ionic compound, electrons are not equally shared. Covalent compounds or covalent bonds have higher electronegativity than ionic compounds. This is because with covalent compounds, they have a stronger attraction to the electrons that are shared. Polarity is defined as the difference of electronegativity values. These values, as you will see in the discussion problems that we go over, these values can be found on page 189 on table 6.7. There's a chart for each and every value that tells you whether each and every bond is non-polar covalent, polar covalent, or ionic. If the values fall between 0.0 and 0.4, it will be classified as non-polar covalent. 0.4 or less than 1.8, polar covalent. And if it is greater than 1.8, it will be ionic. Two problems we have here are bond of silicon and oxygen, and potassium and chlorine. First, let's look at silicon and oxygen. Silicon has an electronegativity value of 1.8, and oxygen has one of 3.5. Take 3.5 minus 1.8, and you have 1.7. 1.7 falls under the polar covalent value. Potassium and chlorine. Potassium has 0.8, and chlorine has 3.0. 3.0 minus 0.8 will give you 2.2, which falls under the ionic compound.
Topic 6.7, shapes and polarity of molecules. This is just a definition, the valence shell electron pair repulsion. It's basically the electron groups are arranged as far apart as possible around the central atom to minimize the repulsion between negative charges. And these are just some types of electron groups. They have like 2 electron groups, which mean they have like double bonds. They're most likely to be linear, and their degree angle is 180. They have 3 electron groups. They mostly come in 2 double bonds, 1 double bond. The degree angle equals to 120, and they kind of are triangular polar. Or they can also come as 1 single bond, 1 double bond, and 1 lone pair electron. There can be sometimes be shaped as bent, and the degree angle can equal up to 120 also. And also another example of electron group is 4 electron groups. They have 4 single bonds. They are tetrahedral, and their degree angle equals to 109. Okay? Now we're coming over to the nonpolar molecules and the polar molecules. The nonpolar molecules are bonds that are nonpolar or polar bonds that did not cancel out. Some example would be H2, Cl2, or Cl2. Diploids cancel out because they're symmetrical arranged. And the polar molecules, they have like one end of molecules that is more negative than the other end. They occur when individual diploids do not cancel out, and some examples are HCl. It only has 1 covalent bond, and that one is polar. Molecules with 2 or more electron groups often also be polar molecules. Another example would be H2O, because individual diploids do not cancel out. Okay, so I have a problem over here on how you can find out the shape of a formula. I have SCl2. To predict the shape, you mostly have to find out the name of the element, how many atoms are in the formula, the valence shells, and how many total electrons you have to put on the shape. So I have sulfur and chlorine, which is S and Cl. It's only 1 atom of sulfur, 2 atoms of chlorine, 6 atoms of valence shells, and 7 of chlorine, so that equals up to 20 electrons. Basically, all I did was put the 2 Cl atoms and the 1 sulfur atom in the middle, because there's only 1, and I just put the electrons all around the shape, which will equal up to a linear shape. And it is linear because it has 2 bonded atoms and no lone pairs. And that concludes